Let's first take up the concept of Kepler's laws of planetary motion. So there are three laws, namely the law of orbits, the law of area, and the law of time periods. Now, the law of orbits. Every planet moves around the sun in an elliptical orbit with the sun at one of the foci. Every planet moves around the sun in an elliptical orbit with the sun at one of the foci. For ellipse, we define two focal points, and here the sun is said to be located at one of the focus points, and the planet moves around the sun in that elliptical orbit. The point in the elliptical orbit closest to the sun is called Perihelion. This is the point here which is the closest to the sun in its elliptical orbit, and the point in the orbit farthest to the sun is called aphelion. And here the distance from sun to perihelion is r minimum, denoted by r1 here, and the distance from sun to aphelion is the maximum distance, that is r2. Now, semi-major axis of elliptical orbit is r1 plus r2 divided by 2 and is denoted by a. So this parameter semi-major axis is required in our third law, that is law of time periods. So semi-major axis is measured as r1 plus r2 divided by 2, where r1 is the minimum distance, that is sun to perihelion, r2 is the maximum distance, that is sun to aphelion distance. Now let's look at the important points under the law of areas. The line joining the sun to the planet sweeps out equal areas in equal intervals of time. The line joining the sun to the planet sweeps out equal areas in equal intervals of time. That is, the aerial velocity of the line joining the sun and the planet is a constant. It is a consequence of law of conservation of angular momentum that we understand just now. So importantly, remember the Kepler's second law of planetary motion, that is law of areas, is a consequence of law of conservation of angular momentum. Here, the aerial velocity of the line joining the sun and the planet is given to be constant. That is, aerial velocity is dA by dt, and this is, so it means here actually dA is the area that is covered in a small interval of time, dt. Here, corresponding to the angle d theta, dA is measured as half into r into the arc length. Arc length is r d theta. So half into r d theta is dA divided by dt. And this is half into r square into d theta by dt is omega. Now let us multiply and divide with m, this expression. So numerator will be mr square omega divided by 2m. Here mr square omega is I omega, that is L, divided by 2m. So the expression aerial velocity we can write as L by 2m, where L stands for angular momentum of planet, which is given as mr square omega, that is mvr, also I omega, which is a constant. Here as the planet moves around the sun in its elliptical orbit, there is no external torque turning effect. So the angular momentum should be constant, is conserved. So as L is constant, m anyhow the mass of the planet is a constant. Therefore the term L by 2m is constant. That implies aerial velocity is a constant. So dA by dt equal to L by 2m is a constant. So law of areas implies For a planet in an elliptical orbit, the quantity mvr equal to constant. Anyhow, m is being constant, v into r equal to constant. That is, here v maximum into r minimum should be equal to v minimum into r maximum. V maximum into r minimum is v minimum into r maximum. That is, the planet in an orbit moves slowly when it is at the farthest distance from the sun and moves more rapidly when it is nearest to the sun. The speed of the planet is most when it is nearest, that is at perihelion, and least when it is at the farthest point, that is at aphelion. So the product v into r is a constant. And then let's look at the important points under the heading the law of time periods. The square of the time period of revolution of a planet around the sun is directly proportional to the cube of the semi-major axis of the orbit. The square of the time period of revolution of the planet around the sun is directly proportional to the cube of the semi-major axis of the orbit, that is t square proportional to a cube. And already we understand earlier, a, the semi-major axis, is r1 plus r2 by 2. Therefore we can write the expression as t square proportional to r1 plus r2 by 2 whole cube, where t is time period of revolution of planet around the sun, a is semi-major axis of elliptical orbit, r1 is distance of planet from the sun when it is at a perihelion, and r2 is distance of planet from the sun when it is at aphelion.